Last up is Russell Gilabert from NASA Langley. He's a computer science research engineer over there. Master's degree in electrical engineering from Ohio University. Current research focuses are on the global navigation satellite systems like GPS, their system performance, and the dependable navigation for autonomous aerial vehicles. Very cool. All right.
Thank you for the introduction, and thank you for attending the last talk of this session. My name is Russell Gilabert, and today I'll be presenting work performed by myself, as well as Julian Gutierrez and Evan Dill on simulated multipath using software-generated GPS signals. So a brief outline for this presentation. We'll go over the background, experimental setup, followed by the results, conclusion, and then finally the future work. So if you think about GPS tends to work fairly well in open environments where you have good satellite geometry and direct line of sight to the satellite signals. However, things start to change when you start to operate in an urban environment such as a city. So you get the buildings start to degrade your performance. They block signals, they can reflect signals, and this can result in reduced satellite availability. So you lose measurements as well as multipath of some of those measurements. The signals will travel different routes on their way to your receiver, and this can be very detrimental to your position. And this can be one of the largest error sources contributing to degradation in GPS performance in this type of environment. So before we dive into multipath, I want to take a step back and talk about how GPS works fundamentally. So it works by multilateration. A user is able to determine their distance to a satellite, and they know where that satellite is. So essentially, they can determine that they are on a circle in 2 dimensions or a sphere in 3 dimensions away from a particular satellite. Now, if you've got multiple measurements to multiple satellites, you can determine your location by where those circles or spheres intersect. It's a little bit more nuanced than that, but that's a good general concept. Now, how do you get that range to the satellite, right? So the satellites transmit what's known as PRNs, the pseudo-random stream of numbers. And these are pseudo-random because they're known. So the receivers all know what each satellite is broadcasting. So they can run a local stream of those numbers and then compare their local stream to what they're seeing from the satellites, line these up in time, and get a time offset. And if you know the time offset, you can estimate your range and produce what's called a pseudo-range. And this tends to work fairly well under ideal circumstances. However, once you start to operate in an urban environment, you get these bounces and reflections of your signals, and this can contribute to your error sources, right? So the receiver will see all of the multipath, and it will view each of these reflections as a composite of everything put together. So when your receiver tries to correlate, it will correlate on the composite of what it sees, and this typically results in a delay of your measurement. And so a delay in time equals a length in distance. So this is what's happening. And this can vary greatly depending on the conditions, depending on your operating environment, but depending on your user equipment as well. So if we could simulate this multipath, we could evaluate different receivers and look at their multipath resistance, put them in various scenarios and see what their operational limitations and behaviors are. And this would assist us in developing multipath mitigating technologies. Now, commercial GPS simulators do exist. You can purchase them, but they are oftentimes very expensive, and they can have limited out-of-the-box tuning capabilities. If I want to add specific multipath and test a specific scenario with specific signals, this could be limited depending on what's supported by the device. So the question and what we are going to be looking at in this presentation is, can we modify open source tools to add this capability, add a multipath simulation. So the tool we're going to be looking at is called GPS-SDR-SIM. It is a command line open source tool that allows a user to input satellite ephemeris, so the satellite orbits they'd like to simulate, as well as the coordinates of the position they would like their solution to converge at. And the output of this is a binary file, which contains the RF information of your simulated data. Now, this can be played back by, on a real receiver or a software-defined receiver for evaluation. And so what we've done, these are the capabilities out of the box. We've added the ability to clone a satellite's PRN, so duplicate the satellite, and then delay that PRN by a precise variable amount. And the ultimate goal of this is, so can we recreate multipath characteristics, this multipath composite signal that a receiver would see? So that's the goal. Those are the modifications that we've done. We've tested this on 2 different devices. One of them is a software device. It is another open source tool called GNSS SDR, which allows us to take in the file that we've generated, this binary file, and produce a position solution as well as pseudo range measurements. So this allows us, it's all in software, all command line. We can rapidly test and iterate using this. And then we took it a step further and implemented this in hardware. So we can play back our binary file on a software-defined radio. In this case, we use a HAC RF1 and connected that up to a U-Blocks receiver, allowing us to get the resulting pseudo-range measurements as well as its final solution. So for this, we had 3 different tests where we just simply delayed a signal, and this is for G1 is the satellite that we made these modifications to. We delayed the signal for G1, then we synchronized the signal, so we had it produce its normal signal, and then we duplicated that signal and overlaid them in lockstep on top of each other to make sure we're not garbling any messages, the receiver still sees it. And then we attempted to create a multipath signal. So we have the original signal at time 0, and then we add another signal at a delayed time, and we see how the receivers react to it. And again, ultimately to try to recreate this composite multipath. We took another satellite, G2, and because this is a simulation, we can place this satellite wherever we like, and we put it at the exact location as G1. So it's our baseline measurement. Everything that we do, we can compare G1 to G2 and see what the impacts are of our modifications. And we tested this in software with GNSS SDR and in hardware with our U-Blocks receiver. So moving on to the results. So for the delayed signal, we delayed G1 by 20 meters. There's no cloned broadcast here, and we compare this against G2 in the same orbit. If we take a look at a single epoch, see that there is a difference of about 20 meters between G1 and G2. And if we look at the data over the entire data set, which is about 600 seconds, on average, we can see there's about a 20-meter difference between the 2 satellites, which is great. It's what we had put in there. So it's what we should expect to see. So it looks like this is working properly. And for fun, we can take a look at the histogram here and see that we're seeing a largely Gaussian distribution on our data. So the next step is to clone the PRN for G1. So we have it broadcast its original signal, then we have our clone and lockstep. What should happen is there should be no interference here. Our receiver should be able to detect G1 as normal. It should still see G1. And we compare our measurement to G2. And again, here we see that they're very similar measurements. It's off, the single epoch is off by maybe a meter. And if we look at the entire data set of 600 seconds, we see on average we're around 0 meters. Which is what we would expect. So this case looks good too. And again, we see a largely Gaussian distribution on our data set. So lastly, we want to attempt to create a multipath signal. So we have 0 meter delay on G1, and we add another signal. So this is G1 again with a 20 meter delay, and we compare what the receiver sees relative to G2. So what's this going to look like? That's the question. If we take a look at a single epoch, it looks like there is about a 10-meter difference between these two. And if we look at the entire data set, on average, the difference between these two satellite measurements is about 10 meters, which is interesting because we don't have 10 meters anywhere. But this is an interesting, good result. It looks like we are recreating characteristics of multipath here on the receiver side. We have our initial 0 delay on G1, and then our 20-meter delay on the other side. And it looks like our receiver is correlating right in between those two measurements, which is consistent in what we would expect to see in real-world multipaths. That's a very exciting result. And again, the distribution on here appears to be largely Gaussian. So far, we've tested in simulation, our delayed signal, synchronous signal, and a multipath signal, and they appear to be working as expected. So the next steps are to repeat this in hardware. And I want to, here, this is where we took the binary file, played it back with our SDR, connected up to our U-Blocks GPS receiver. So I want to emphasize that these are preliminary results, and working with hardware can be somewhat more nuanced. I contemplated including these results in the presentation, but I think it's interesting to show where we are in our research. And given the talk this morning, it's interesting to see how things vary from simulation to implementation in hardware. So testing is very important. So with that in mind, we'll take a look at the delayed signal. This is where we had 20 meters delay on G1 with no cloned broadcast, and we compare this to G2. And these are the results. They're not exactly as expected. They look a little odd. They jump around, and there's a large magnitude between the two. So what it appears is happening are we're having clock stability issues on our software-defined radio, and they seem to be particularly problematic after 40 to 60 seconds of data. So GPS satellites have atomic clocks that are highly synchronized, very accurate, and we are using COTS software-defined low-cost receiver, software-defined radio. So it's likely that we don't have the clock stability that we would have in an actual constellation. However, if we limit our analysis to the first 30 seconds, this may be sufficient to at least get some preliminary sense of how this is performing. So for this case, if we repeat it and only look at the first 30 seconds of data, we're seeing on average about a 19-meter difference between the two measurements, which is very similar to what we were seeing in simulation. Now, if we move on to the next one, this was the synchronous case where we are just cloning the measurement. Again, we see similar oddities here if we look at the entire data set. But if we zoom in and focus on the first 30 seconds, we see around a -1, very close to 0, which is what we would be hoping for or expecting in this particular case. And lastly, if we move on to the multipath data set, again, very similar oddities, looking at the entire time length here. And again, this is the case where we have a 0-meter delay followed by a 20-meter delay of a cloned broadcast simulating a bounce. If we compare this to G2 in the same orbit, we're seeing an average of 11 meters. So this, again, is very similar to what we were seeing in simulation, where we had almost exactly 10, or quite close to 10 meters. So again, this looks like we are we're able to recreate multipath characteristics on the receiver side, and we're correlating right between our two signals that we're producing. So on to the conclusions here. It appears that the modifications that we are making to GPS-SDR-SIM are successful. We can duplicate PRNs and add arbitrary biases to them. Our simulation confirms that our proof of concept is working, and our hardware results at least show that the PRNs that we are producing are functional and have similar, although we are experiencing some clock stability issues, the beginning of the playback does seem to reproduce what we are seeing in simulation. So this is a very promising result. So still more work to do. Looking at our future work, I want to look at ways to achieve better clock stability with our hack RF1, get rid of these oddities, and look at a longer data set for better results. The hack RF1 has the ability to be fed by an external clock source, so I want to explore that and see if we can get better clock stability through that method. So once we have that working, we can reassess the hardware performance of this of a physical GNSS GPS receiver and verify what we're seeing in simulation to a better degree. And then lastly, fine-tune some scenarios, right? We want to test these GPS receivers under different varying multipath scenarios and conditions and see how they respond. And that is the end of my talk. Thank you all for coming.
Jason Schloop, IDA. If you go back to your traces that you had, the clock stability issues, it appeared, one more, there we go. So it appears that you have a couple of plateaus, for lack of a better word. You selected 0 to 30 seconds. What would you expect to happen if you selected like 100 seconds to 120 in that plateau, or any of the subsequent ones? Would you expect similar results, or do you have to rely on that initial time period of your sample? So
it appears that at the beginning of the data set, it's more stable, or the correlator, the GPS receiver itself is doing a better job of converging on a solution. And it seems to be doing this in waves, right? It's tracking, it's doing very well, and then it falls apart, and then it retracks. It seems like the longest area of stability is right at the beginning of the data set. That's why I chose to limit my analysis to that location. It does seem to vary, right? It seems to bounce up and down, and those areas don't seem to correlate with what we're seeing in simulation. So I figured them to be more erroneous locations. But the beginning does seem to reproduce what we're seeing in simulation.
Yeah, I have one question. And correct me if I'm wrong. So did you build hardware? Are you actually radiating things to a receiver in the physical space in this experiment?
I don't know if radiating is, yes, radiating. It's a direct connection. There is no, I might have used the word broadcast. We are not broadcasting in the physical space. It's a direct connection.
Understood. Because I think you're modeling an urban environment, but it sounds like you're also spoofing GPS signals in a way, right? Is that correct?
So we are recreating the GPS signals. I don't know if spoofing is the right word to use.
So that's why I hesitated to say spoof.
Yes.
You're modeling a real GPS satellite location and signal.
Yes.
And you're adding some sort of offset to add error or change where you're supposed to be reading your location. Is that right?
Correct. Yes.
Okay. Got it. I guess that's the extent of my question, is how this could be applied for academic purposes, as you show here, and otherwise. Got it. Okay. Thank you. Anything else? Cool. Okay. Let's thank our speaker.
Thank you.